The star closest to Earth just showed us something that does not fit. Alpha Centauri sits 4 light-years away, our nearest neighbor in the entire universe. James Webb pointed at it, and the images came back wrong. Extra heat, a vanishing light point, a dust pattern that should not be there. We are going to walk through every piece of it, what Webb actually detected, why scientists are arguing over the data right now, and what it could mean for life beyond Earth. If you enjoy this, subscribe and hit like. Let's go. Alpha Centauri is right there, 4 light-years away, the closest star system to Earth in the entire universe. You could draw a straight line from our Sun to Alpha Centauri, and nothing else would be in the way. No other star system sits closer to us. Of all the hundreds of billions of stars in our galaxy, this is our next-door neighbor. And for decades, we pointed our best telescopes everywhere except at it. That sounds strange. It sounds like ignoring the house next door to study buildings on the other side of the city. But there was a reason, a real technical reason, and understanding it is the first step to understanding why what Webb just found is so surprising. Alpha Centauri is not one star, it is 3. 2 of them, called Alpha Centauri A and Alpha Centauri B, orbit each other so closely that from Earth they look like a single bright dot in the southern sky. They are bright, almost painfully bright for a space telescope. Imagine trying to spot a firefly sitting next to a stadium floodlight. The glare from the 2 main stars would wash out anything faint nearby, smearing the image into useless white. The 3rd star, called Proxima Centauri, sits much farther out. It orbits the other 2 from a distance so large that one full trip around them takes roughly 500,000 years. Proxima is tiny, dim, and violent. We will come back to it. For most of modern astronomy, the brightness problem made Alpha Centauri a scientific blind spot. Hubble avoided it. Ground telescopes could not get clean data. The system was close, but effectively untouchable, like a word on the tip of your tongue that never quite arrives. James Webb changed that. Webb sees the universe in infrared, which means it detects heat rather than visible light. It also has a mirror nearly 22 feet wide, 6 times larger than Hubble's. That combination lets it separate sources of light that are extremely close together on the sky with a precision nothing before it could match. Engineers spent years designing special filters and observation techniques just to handle bright targets without blinding the instrument. In late 2022, the Webb team pointed the telescope at Alpha Centauri for the first time in history. The images came back clean, sharp, detailed in a way no one had seen before from this system. Scientists expected to see 2 bright stars surrounded by the soft glow of surrounding space. A clean, predictable picture. The kind of image that confirms what you already know and lets you move on to the next target. That is not what they saw. The data showed heat signatures that did not match the expected output of the 2 main stars. There was structure around them, faint, organized structure. The kind of pattern that forms when material is gathered into a disk, orbiting a star in a flattened ring. Disks like that are not random. They mean something happened there. Something is happening there. Scientists stared at the data for weeks before saying anything publicly. They ran it through every filter. They checked for instrument errors. They compared it against background readings. The signal held. Alpha Centauri, the star system humanity has looked at since before telescopes existed, was hiding something, and Webb had just peeled back the first layer. What that layer revealed would force scientists to ask a question they had quietly avoided for years. Every major space telescope in history had Alpha Centauri on its avoid list. That sentence deserves a pause. The closest star system to Earth. The one place beyond our solar system humanity has dreamed about visiting since we first understood what stars were. Deliberately skipped, flagged as off-limits, marked in observation catalogues with a warning. The reason starts with brightness. Alpha Centauri A and B together form one of the brightest objects in the southern sky. They sit in the constellation Centaurus, visible from places like Australia and South America. burning with a combined light that makes them the third brightest star-looking object in the entire night sky, after only the Sun itself and Sirius. To the naked eye, they appear as a single glowing point. Beautiful, familiar, easy to find. For a space telescope, that brightness is a hazard. Hubble's detectors worked like a digital camera sensor. Point a camera sensor directly at a stadium spotlight, and you do not get an image of the light. You get a white smear that bleeds across the whole frame. Every pixel in that zone becomes useless. Astronomers call this effect saturation. The detector fills up with photons faster than it can process them, and the data becomes noise. Alpha Centauri would have saturated Hubble's detectors in seconds. But the brightness problem runs even deeper. Telescopes searching for faint objects near stars, like planets, dust clouds, or heat signatures, need to block the star's direct light to see anything around it. They use a device called a coronagraph, essentially a tiny mask placed inside the telescope that covers the star's disk and blocks its glare. This works well for moderately bright stars at useful distances. Alpha Centauri was too bright and too close for coronagraphs to help. The glare still leaked around the edges of the mask. The data still came back contaminated. So the scientific community made a quiet, practical decision. Alpha Centauri was not worth the instrument risk and wasted observation time. Move on to other targets. Study the thousands of star systems farther away where the numbers work better. Decades passed. A generation of astronomers built careers studying stars hundreds and thousands of light years away, while the closest one sat overlooked. Webb changed the math. Webb's infrared sensors operate differently from Hubble's optical cameras. Infrared light carries heat energy rather than visible wavelengths, and Webb's detectors process it without saturating as rapidly. Engineers also built Webb with a set of specialized filters specifically designed for extremely bright targets, allowing the telescope to dim incoming signals before they hit the sensor. These filters work the way sunglasses work, cutting down the raw intensity without destroying the information hidden inside it. The Webb team developed a custom observing strategy for Alpha Centauri. They used short exposure times, rapid readouts, and layered the data from many brief snapshots rather than taking one long exposure. They tested the approach before committing to it. It worked. For the first time, a space telescope could look directly at Alpha Centauri and come back with clean, scientifically usable data. The blind spot that had lasted for 50 years of space telescope history closed in a single observation run. What waited inside that blind spot had been sitting there the whole time, and the data that came back was not what the models predicted. Something around Alpha Centauri was emitting heat it had no obvious source for. The question of where that heat was coming from would pull scientists into a debate that is still unresolved today. Most people picture Alpha Centauri as a single star. It is 3. That fact alone changes everything about this system. A single star like our Sun sits at the center of its solar system like a campfire in the middle of a field. Everything orbits it in predictable, stable paths. Planets form, settle into their lanes, and stay there for billions of years. The physics is relatively clean. 3 stars sharing a system creates something far messier. Alpha Centauri A and B are the main pair. They are similar to our Sun, both yellow and orange stars burning with steady nuclear fire. Alpha Centauri A is slightly bigger and brighter than our Sunday. Alpha Centauri B is slightly smaller and cooler, closer to a deep orange glow. They orbit each other on an oval-shaped path, sometimes pulling as close as the distance between our Sun and Saturn, then swinging apart to nearly the distance between our Sun and Uranus. One full orbit between them takes about 80 years. From the surface of a planet orbiting one of these stars, the sky would contain 2 suns. On certain nights, the second sun would be bright enough to cast shadows. Then there is Proxima Centauri. Proxima sits about 13,000 times farther from the main pair than Earth sits from our Sunday. At that distance, it takes roughly 500,000 years to complete one orbit around A and B. Some astronomers have debated whether Proxima is even gravitationally bound to the system at all, or whether it just happens to be drifting through the same region of space. Current measurements suggest it is connected, but barely, held by a gravitational thread thinner than anything we have in our own solar system. Proxima is a red dwarf, small, dim, and extraordinarily violent. Here is why the three-star setup makes Webb's findings so complicated. Gravity from two massive stars pulling at a planet from slightly different angles creates instability over long time periods. Scientists ran simulations for decades, trying to figure out where a planet could survive in this system long enough for life to develop. The answer is a narrow band around each of the main stars, close enough to that star to stay warm, far enough from the other star to avoid gravitational disruption. That band exists. It is tight, but it exists. The debris disk Webb detected sits inside or near that band around Alpha Centauri b. A debris disk forms when small, rocky bodies, think asteroids and comets, grind against each other over millions of years and produce dust. The dust catches starlight and re-emits it as heat. Webb sees that heat. The disk's position, its shape, and its temperature all carry information about what else might be sharing that orbital space. The shape of the disk around Alpha Centauri b has a clean inner edge, an empty zone right where a planet would sit. Clean edges in debris disks do not appear randomly. Something with gravity carves them. A planet sweeping through that zone clears the debris as it orbits, like a broom pushing dust aside, leaving a gap at its orbital path. Webb cannot directly photograph a planet there. The planet, if it exists, would be too small and too dim, even for Webb's extraordinary vision. But the disk is speaking. Its shape is a message. Scientists just have to figure out how to read it. And one piece of that message, the temperature profile of the disk itself, does not match any model they have for a simple, quiet debris ring. Something is adding heat from a source they have not identified yet. Infrared astronomy sounds complicated. The basic idea is simple. Everything with a temperature above absolute zero emits infrared radiation. Your body does it right now. A warm cup of coffee does it. A rock sitting in sunlight does it. Stars do it constantly and powerfully. Infrared is just heat energy moving through space as waves. Webb's primary mission is to detect those waves from sources billions of light years away. Galaxies forming in the early universe. Stars being born inside clouds of gas. The faint chemical fingerprints of atmospheres around distant planets. Webb does all of this by collecting infrared light with its massive golden mirror and focusing it onto sensors cooled to nearly -450 degrees Fahrenheit, colder than anything that occurs naturally in the solar system. That extreme cold is necessary because a warm detector would drown out the faint signals Webb is hunting. When Webb looked at Alpha Centauri, it measured the infrared output of both main stars very precisely. Every star emits a predictable spectrum of heat. Scientists know the temperature of Alpha Centauri A and B from decades of ground-based measurements. They know how much heat each star should be putting out at every infrared wavelength. They can calculate the exact signature Webb should detect, down to very fine detail. The measured signature did not match the calculation. Around Alpha Centauri b, Webb detected excess heat at specific infrared wavelengths. The star itself accounted for most of the signal, but there was a leftover glow that the star's known temperature and size could not explain. That excess sat in a region of the spectrum associated with warm dust, material heated to temperatures between a few hundred and a few thousand degrees Fahrenheit. Warm dust means a debris disk. Scientists expected some dust. Debris disks are common around middle-aged stars. The problem was the intensity. The excess heat Webb measured was stronger than debris disk models predicted for a system at Alpha Centauri b's age and distance. Alpha Centauri b is roughly 5 billion years old, similar to our Sunday. At that age, debris disks typically thin out. Most of the collisions that generate fresh dust happened billions of years earlier. The system should be relatively clean by now. Webb found a disk producing far more heat than a 5-billion-year-old system should generate from random asteroid collisions alone. Something is stirring the debris. Some gravitational force is driving fresh collisions in that disk, keeping it active and warm long past the point where it should have settled down. 3 candidates sit on the table. First, a planet in a slightly oval orbit could be sweeping through the disk periodically, knocking asteroids into each other each time it passes. Second, the gravitational influence of Alpha Centauri A, pulling on the disk from across the system, could be pumping energy into the orbits of debris and forcing collisions. Third, something in the inner zone of the disk, a body too small for Webb to detect directly, could be generating the stirring from close range. Each of these explanations carries a different implication for what else might be inside that system, and one of them, if correct, would place an active, geologically alive planet in the zone where liquid water could pool on a surface. Scientists have not confirmed which explanation is right, but the heat is real, the excess is real, and something is producing it 4 light-years from Earth. Dust tells a story. In our own solar system, the space between the planets is not empty. It is filled with tiny particles of rock and ice, remnants from the early days of planet formation 4.5 billion years ago. Most of the large collisions that created that dust happened in the solar system's youth. Today, the asteroid belt still produces some new dust from slow grinding collisions, but the overall level is low. Our solar system's debris disk is thin and faint. Alpha Centauri B's debris disk is neither. Webb measured the disk's heat output and compared it to the baseline expected for a system its age. The excess was significant enough that scientists immediately started asking what was driving it. A disk this warm and this active at 5 billion years old needs a reason. To understand why that matters, think about what a debris disk actually is. When a planetary system forms, a spinning cloud of gas and dust collapses inward toward a new star. Most of the material either falls into the star or gets swept up into forming planets. But a large fraction stays behind as smaller bodies, asteroids, comets, and chunks of rock that never made it into a full planet. These objects grind against each other slowly over billions of years. Each collision produces fresh dust. That dust catches heat from the star and radiates it back into space as infrared light. Webb sees that infrared glow and can measure its intensity. The shape of the glow carries information. A disk spread evenly in all directions around a star produces a different heat pattern than a disk concentrated in a narrow ring. A disk with a hole punched in its inner zone produces yet another pattern. Webb's data on Alpha Centauri B shows a disk with structure, a concentrated ring of warm material at a specific distance from the star, with a cleaner, emptier region closer in. That inner gap is the key detail. Gaps like this form when something with gravity sweeps through the disk repeatedly, clearing debris out of its orbital lane. In our own solar system, Jupiter does this constantly. Its gravity dominates the asteroid belt, keeping the region from accumulating too much material and preventing the leftover debris from reassembling into a new planet. A similar process appears to be happening at Alpha Centauri B. The swept zone sits at a distance from the star that places it inside what scientists call the habitable zone, the region where a planet's surface temperature could allow liquid water to exist. The gap is not a small one. It spans a range consistent with a planet in a roughly Earth-sized orbit, taking somewhere between 200 and 400 days to complete one trip around the star. Scientists cannot see the planet. Webb's resolution at 4 light-years is extraordinary, but still limited when searching for something planet-sized. What they can see is the absence of debris where that planet would sit, and the warm, active ring just outside it, where the swept material piles up. An invisible object is announcing itself through the shape of the dust it pushes aside. Whether that object is a barren rock or something far more interesting, the data does not say yet. What the data does say is that the system around Alpha Centauri B is alive in ways that should have quieted billions of years ago. A planet does not send out a signal saying it exists. It announces itself through what it does to everything around it. Its gravity pulls at nearby objects. It sweeps debris from its path. It carves gaps and rings into the material orbiting its star. Scientists learned to read these signs the way a detective reads a room, not by finding the thing directly, but by finding everything the thing disturbed. Debris disk astronomy became one of the most powerful, indirect planet hunting tools available, long before Webb launched. The logic is clean. If you throw a ball through a pile of sand, the ball leaves a tunnel through the sand even after it has moved on. A planet moving through a debris disk does the same thing on a much larger scale. It clears a path. And because the planet keeps orbiting, it clears that path continuously, maintaining a gap as long as it exists. The first strong evidence that this technique worked came from a star called Beta Pictoris, about 63 light-years from Earth. In the 1980s, astronomers found a bright debris disk around it with a noticeable warp and inner clearing. Scientists argued for years about whether a planet was causing the shape. In 2009, direct imaging confirmed it. A giant planet sat exactly where the disk's structure suggested one should be. The debris disk had pointed directly at a planet before any telescope could photograph it. Alpha Centauri B's disk is now telling a similar story. Webb's infrared measurements show the disk's heat concentrated in a ring at a distance, where temperatures could allow liquid water on a rocky planet's surface. The region interior to that ring shows less material than the region just outside it, consistent with a body sweeping it clear over a long period of time. The team working with Webb's data modeled what kind of object could produce the observed gap. A planet roughly 1 to 3 times Earth's size, in an orbit taking roughly 200 to 400 days, fits the shape of the disk well. A much smaller object would not sweep a gap this wide. A much larger one would have disrupted the outer ring into a different pattern. The mass range that fits the data overlaps almost exactly with what scientists call a super-Earth, a rocky planet larger than Earth, but smaller than Neptune. The category scientists now believe is the most common type of planet in the galaxy. Super-Earths can hold atmospheres. They can have liquid water. Several that orbit other stars have already had their atmospheric chemistry studied by Webb. The results on those distant worlds, hundreds of light years away, have been mixed. Some show chemical hints that are intriguing. None have been confirmed as life-bearing. A super-Earth at Alpha Centauri b would be the closest one ever identified. It would sit close enough to Earth that a radio signal sent toward it today would arrive in 4 years. That proximity changes the nature of the question. Studying an exoplanet 4 light-years away is fundamentally different from studying one 400 light-years away. Not just in scientific detail, but in what humanity could eventually do about whatever it finds. The debris disk is not proof of a planet. It is a strong, structured suggestion, a shape that demands an explanation, and that has one very clean answer sitting in the middle of it. The debris disk was already strange enough. Then scientists noticed something on top of it. When Webb measured the infrared emission from the region around Alpha Centauri b, they expected to find 2 main sources. First, the star itself, radiating heat from its surface. Second, the debris disk, re-emitting heat absorbed from the star. Both sources have predictable signatures. Both can be modeled with high accuracy. After accounting for both, a residual signal remained. This residual is not enormous. It is a subtle excess above the expected total, showing up at specific infrared wavelengths. But Webb's instruments are sensitive enough to measure it clearly. It sits in a part of the spectrum associated with temperatures between roughly 200 and 600 degrees Fahrenheit, warmer than the outer debris ring but cooler than the star's surface. That temperature range points toward material sitting close to the star, inside the orbital zone where the debris disk has its inner gap. To understand what that means, consider what produces infrared emission at those temperatures. Warm rock does. Volcanic surfaces heated by a star's radiation glow in this range. Dense atmospheres that trap heat and redistribute it also emit in similar wavelengths. So do active geological processes, volcanic eruptions, hydrothermal vents, tectonic friction. A planet with any of these features would produce a heat signature in the exact range Webb detected as excess. Scientists are careful about saying this directly, because the signal could also come from diffuse material scattered in the inner disk region, tiny grains of dust heated more intensely by their proximity to the star. Both explanations are consistent with the raw numbers Webb recorded. But there is a complication. The inner region of the disk, the gap zone, should be nearly empty if a planet is sweeping it clean. Dust grains in that zone would be pulled onto the planet, absorbed into the star, or scattered out of the area on short timescales. For significant diffuse dust emission to persist in that zone, something would need to continuously replenish it. That replenishment could come from volcanic activity. A geologically active planet constantly sheds fine material into its surrounding space through eruptions and impacts with small bodies. This material drifts into a cloud around the planet, heated by the star, and emits infrared light. A geologically active planet in Alpha Centauri B's habitable zone would produce exactly the residual glow Webb measured. Scientists have not confirmed this interpretation. They have not eliminated it either. What they have established is that the extra heat is real, located in the right zone, at the right temperature, and consistent with a warm, geologically alive body sitting 4 light-years from Earth. The search now requires a different kind of measurement, one that Webb was not originally designed for but has proven capable of performing in extraordinary ways. Because if that planet has an atmosphere, and if that atmosphere contains the right chemistry, Webb might be able to see it. That possibility is what drove the next phase of the Alpha Centauri investigation, and what the team found when they looked for atmospheric signatures changed the internal debate inside the science group entirely. James Webb's mirror is the reason this discovery happened. Before getting into what Webb found, it is worth understanding exactly how different this telescope is from everything that came before it. Because the gap between Webb and its predecessors is not a small improvement. It is a leap that changes what questions astronomy can even ask. Hubble's primary mirror measures about 7.5 feet across. For 30 years, that mirror was the gold standard of space astronomy. Hubble gave humanity the deepest images of the universe ever taken, revealed the expansion rate of the cosmos, and photographed galaxies so far away their light left before Earth existed. 7.5 feet of mirror did all of that. Webb's mirror measures nearly 22 feet across. That difference in size translates directly into collecting power. A bigger mirror gathers more light from the same source in the same amount of time, the way a bigger bucket collects more rain. Webb collects roughly 6 times as much light as Hubble per second of observation. For faint targets, that means Webb can detect sources Hubble would never see at all. But the size is only part of the story. Webb's mirror is segmented. It is built from 18 hexagonal panels made of a metal called beryllium and coated in a thin layer of gold. Gold reflects infrared light better than any other material available at the precision Webb requires. The panels fold for launch, then unfold and align themselves in space, guided by tiny motors that adjust each panel to within a fraction of the width of a human hair. The alignment has to be that precise, because Webb is not just collecting light, it is combining light from all 18 panels into a single, coherent image. If any panel is off by even a tiny amount, the image blurs and the instrument loses sensitivity. The alignment process after launch took months and had to be performed entirely by software and remote commands from Earth. It worked. For Alpha Centauri specifically, Webb's angular resolution, meaning its ability to separate 2 points of light that are very close together, made the observation possible in a way no previous telescope could achieve. The 2 main stars of Alpha Centauri sit close together in the sky from Earth's perspective. Previous telescopes saw them as effectively merged. Webb separated them cleanly and studied each one individually. More importantly, Webb's sensitivity allowed it to detect heat signatures a tiny fraction as bright as the stars themselves. The debris disk around Alpha Centauri b emits heat at roughly 100,000ths the intensity of the star it orbits. Detecting it requires the equivalent of spotting a single lit match sitting next to a bonfire from across a football field. Webb did that. The mirror that made it possible took over 20 years and roughly $10 billion to design, build, test, and launch. It had to survive a rocket launch, generating vibrations intense enough to shake loose components that no human hand could ever reach to fix. It had to unfold perfectly in the cold of space, 1 kilometer from the rocket that carried it. Every component worked, and when it turned toward Alpha Centauri b and measured the heat coming from the space around that star, it found something that required an explanation no one had yet written. Gravity in a 3-star system is a war. Every object in the Alpha Centauri system gets pulled in multiple directions at once. Alpha Centauri A pulls on Alpha Centauri b. Both pull on Proxima. Proxima pulls back on both. Any planet caught in the middle of that gravitational tug-of-war has to occupy a very specific lane to stay alive long-term. Scientists calculate these stable zones using a concept called orbital mechanics, the mathematics of how gravity shapes the paths objects take through space. For a planet to survive for billions of years in a multi-star system, its orbit has to be tight enough around one of the stars that the other star's gravity cannot slowly stretch and warp that orbit into something unstable. For Alpha Centauri b, simulations show a stable zone extending from roughly half the distance of Earth from our Sun out to about 1.5 times that distance. A planet in a tight, roughly circular orbit anywhere in that range can survive the gravitational influence of Alpha Centauri A across the system without being destabilized over billions of years. That zone and the habitable zone for Alpha Centauri b overlap almost perfectly. The habitable zone, the range of distances where liquid water could exist on a rocky surface, sits between about 80 and 160 million miles from Alpha Centauri b. Earth sits 93 million miles from our Sunday. The equivalent zone around Alpha Centauri b is slightly tighter because the star is a little cooler and dimmer, but the principle is identical. A rocky planet in that zone could maintain liquid oceans. With oceans come the conditions that produced the first life on Earth. The debris disk gap Webb identified sits inside this combined stable and habitable zone. The swept region aligns with where a planet roughly Earth-sized to 3 times Earth's size would naturally clear its orbit. The warm infrared excess sits at the temperature expected for a rocky body inside that zone. 3 independent lines of data all point at the same location in the Alpha Centauri b system. Scientists do not call that proof. They call it convergent evidence. Multiple clues from different measurements arriving at the same answer. But convergent evidence is exactly how major astronomical discoveries have historically worked. Before Pluto was confirmed visually in 1930, its position was predicted purely from anomalies in the orbits of Uranus and Neptune. Before the first exoplanet around a sun-like star was confirmed in 1995, researchers spent years watching a star wobble in ways that demanded a planet to explain them. Alpha Centauri b is wobbling. The debris disk is shaped. The heat profile does not match a simple, empty system. The picture assembling itself from Webb's data is of a star with something orbiting it in the one place in its system where life, as we understand it, could exist. That something may be barren. It may be a dead rock baked by radiation with no atmosphere and no water. The universe is filled with such places, but it may not be. And the distance from Earth to that answer is 4 light-years, the closest it has ever been to us. Alpha Centauri b was supposed to be the boring one. Between the 2 main stars, Alpha Centauri A gets more scientific attention. It is brighter, slightly bigger, and closer in its properties to our own Sunday. If scientists were betting on which star in the pair might host a familiar, Earth-like world, most would have pointed at A. Alpha Centauri b kept coming up in analyses as a secondary consideration. It runs slightly cooler, slightly dimmer, a deeper orange compared to A's yellow-white. Its habitable zone sits closer in. Its light output is more stable, which is actually a point in its favor for life, but it was always treated as the backup option in the system. Webb's data flipped that. The infrared excess around Alpha Centauri b is measurably stronger than anything detected around Alpha Centauri a. The debris disk structure around b is clearer, better defined, and more consistent with an active, dynamically alive inner system. Alpha Centauri a's infrared profile is relatively clean, dominated by the star itself, with a faint, diffuse background disk that matches standard models for a system its age. Alpha Centauri b's profile does not match standard models. That mismatch is precisely what makes it the focus of ongoing scientific attention. The assumption that got broken was a quiet one that most astronomers held without fully articulating it. Stars that are slightly smaller and cooler than our Sun were expected to host quieter, less active debris systems in their middle age. Smaller stars produce slightly less radiation pressure, which drives dust out of inner orbital zones more slowly. The prediction was that Alpha Centauri b's disk would be marginally more present than A's, but structurally similar. A minor difference, not a dramatic one. Webb showed a major difference. The disk around B has structure that B's own stellar properties cannot explain. Radiation pressure from the star does not account for the gap's sharpness. The temperature gradient across the disk does not follow the simple pattern produced by stellar heating alone. Something dynamical is shaping this system, in addition to the star's own output. Scientists revised their models after receiving Webb's data. The revised models that best fit the observed structure require an additional gravitational body in the inner zone, a planet-sized object actively maintaining the gap by sweeping material out of its path on each orbit. The mass and orbital period of that body, derived from the disk's shape and the excess heat's location, falls squarely in the range of a rocky planet with a surface. Alpha Centauri b went from the secondary star to the primary target in one observation run. The science team's attention shifted. Follow-up observation requests were resubmitted with B as the primary target. Analysis tools designed to hunt for atmospheric signatures were pointed at B's orbital zone rather than A's. The whole investigation reoriented around the star that was supposed to be unexciting. That reorientation carried the investigation into territory that no one on the team had initially planned to enter. And the data waiting there, about the system's third star and what it does to the inner zone, forced a rethinking of one of the most basic assumptions in the search for life beyond Earth. Long before Webb launched, a wobble told a story. Detecting planets around other stars is difficult. Direct photography requires blocking the star's overwhelming glare and detecting a planet that reflects only a tiny fraction of its star's light. Only the largest, brightest planets, far from their stars, have been directly photographed, and even those images are usually just single, bright pixels. The more reliable method uses physics. A planet does not orbit a perfectly stationary star. Both the planet and the star orbit their shared center of mass, a point between them determined by their respective weights. For a massive planet like Jupiter, this center of mass actually sits slightly outside the Sun's surface, causing the Sun to trace a small circle in space as Jupiter goes around it. From a distant star looking at our solar system, a careful measurement would see our Sun wobble. This wobble method, called radial velocity detection, has confirmed thousands of planets around other stars by measuring tiny Doppler shifts in starlight caused by the star moving toward and away from Earth as the planet pulls it. In 2012, a team announced something extraordinary. They had detected a radial velocity signal around Alpha Centauri b, consistent with a planet roughly Earth-sized or slightly larger, orbiting the star every 3 days, far too close to the star to be in the habitable zone. The announcement generated immediate excitement and immediate skepticism in equal measure. The 3-day orbit put the planet baking at temperatures far above any possibility of liquid water. But an Earth-sized planet that close to Alpha Centauri b would mean the system could form rocky planets at all, which opened the door to the possibility of additional rocky planets farther out. Then the trouble started. Over the next 2 years, other research groups reanalyzed the same data. They argued the signal was an artifact of the analysis method, a ghost produced by the way the team had processed the measurements rather than a real planet. The original team pushed back. A scientific argument erupted in journals and conferences. By 2015, the consensus had shifted toward the signal being an artifact. The planet was likely never there, or at minimum, the data could not confirm it. But the argument planted something in the scientific community. If Alpha Centauri b could produce a signal that looked like an Earth-sized planet, even a false one, researchers had to take seriously the idea that real planets might exist there. The system became a priority target. Webb's debris disk structure and heat excess arrived on top of that history. The wobble argument was about a planet far too close to the star to be habitable. Webb's evidence points toward the habitable zone. These are different locations, different orbital periods, different classes of evidence. They do not conflict. They stack. The old, unresolved mystery from 2012 is now paired with new, independent evidence from the most powerful telescope humanity has ever built. Two different methods, separated by more than a decade, both pointing questions at the same star. Both saying that something around Alpha Centauri b deserves a closer look. 4 light-years is the number that changes everything about this story. To feel what that distance means, start with something familiar. The fastest spacecraft humanity ever launched was the Parker Solar Probe, which reached speeds of about 430,000 miles per hour during its closest passes by the Sunday. That is extraordinary. Nothing built by humans has ever moved faster through space. At that speed, reaching Alpha Centauri would take roughly 2,000 years. The distance is not traversable with current technology. Alpha Centauri sits at the absolute frontier of what humanity can even imagine reaching within multiple human lifetimes. Every other star system where scientists have found interesting planets sits much farther away. Most sit hundreds of light-years distant. The closest confirmed exoplanet hosting candidates for liquid water sits roughly 40 light-years away, 10 times farther than Alpha Centauri. Alpha Centauri at 4 light-years is a completely different category of target. Consider what that distance means for communication. Radio waves travel at the speed of light. A signal sent from Earth today would reach Alpha Centauri in roughly 4 years. A reply sent immediately would arrive back on Earth 4 years after that. An 8-year round-trip conversation, slow by human standards, but genuinely feasible for long-term scientific exchange if the signal carried something worth exchanging. A probe with current-generation instruments could, in principle, send back basic scientific measurements from Alpha Centauri via radio signal. This is exactly what the Voyager probes do from the edge of our solar system, transmitting data that Earth receives hours after it was recorded. At Alpha Centauri's distance, the same process would involve a 4-year data delivery delay, inconvenient but manageable. Compare that to the nearest other potentially interesting exoplanet systems. A probe transmitting data from 40 light-years away would require an 80-year round trip for a conversation. Multiple human generations would pass between a question and its answer. Alpha Centauri's proximity makes the conversation timescales almost human. Now add the possibility of life. Earth life appeared within roughly the first billion years of this planet's existence. The chemical conditions for life, liquid water, the right mix of carbon and nitrogen compounds, energy from a star, existed and produced something. Alpha Centauri b is approximately 5 billion years old, roughly similar in age to our Sunday. If a rocky planet has sat in its habitable zone for billions of years with liquid water on its surface, the window for life to emerge was roughly the same as Earth's. What might 5 billion years of uninterrupted evolution produce? The question carries implications that extend well beyond astronomy. Every major field of human knowledge, biology, philosophy, religion, history, rests on assumptions about what life is and whether it exists elsewhere. A confirmed detection of biology at Alpha Centauri would not just answer a scientific question, It would rewrite the foundation those fields stand on. That is why Webb's findings around Alpha Centauri b matter beyond the technical detail of a debris disk and an infrared excess. The data is pointing toward the place where that question might, for the first time in history, receive an answer. Debris disks and heat anomalies were already a full scientific story. Then the images showed something else. When Webb's team processed the full dataset from their Alpha Centauri observations, they found a faint ring of light surrounding one of the main stars at a specific distance. Faint rings of scattered starlight appear occasionally in telescope images and are usually explained as reflections of dust or ice particles in the surrounding disk. That explanation was the first one the team applied. It did not hold. The timing was wrong. Webb did not observe Alpha Centauri in a single session. It observed the system across multiple separate windows, separated by weeks. When scientists compared the ring's brightness across sessions, they noticed it was not constant. The ring appeared brighter in the second session than in the first. Reflected light from a stable dust ring does not change brightness over weeks unless the ring itself is changing shape. A stable debris disk is a steady structure built up over millions of years. It does not pulse brighter and then back down on a timescale of weeks. If the ring was reflecting starlight, it should have been steady. It was not. The team looked for other explanations. An increase in stellar output from Alpha Centauri A, more light from the star flooding the disk, could cause the ring to appear brighter. But the star's own measured brightness did not change between sessions. The star was steady. The ring around it was not. A phenomenon called a light echo can cause exactly this kind of delayed brightness change in a ring structure. A light echo happens when a brief flash of intense light from a central source travels outward through space and illuminates surrounding material at different times depending on the geometry. Material at a greater distance from the source is illuminated later than material close in. For a ring of material sitting at a specific distance from the star, a pulse of light from the star would reach it and cause a brightness spike with a predictable delay. The delay depends on the ring's distance and the speed of light. The timing of the brightness change Webb observed between sessions matches the expected delay for a light echo bouncing off material at the distance where the ring appeared. A light echo requires a pulse of intense light from the star. Stars produce pulses through flares, sudden eruptions of magnetic energy from the stellar surface that release enormous amounts of light and radiation in a short period. Alpha Centauri A is a relatively quiet star. It does not flare frequently, but it does flare occasionally, and Webb's observation windows were not continuous. A flare could have occurred between sessions, produced a pulse of light that traveled out to the ring, and caused the brightness increase Webb detected in the second session. The math closes. The geometry works. The timing is consistent. But proving this interpretation requires catching the star in a flare and tracking the light echo as it travels outward. A measurement no-current telescope has been set up to perform at Alpha Centauri specifically. The ring is real. The timing anomaly is real. The most coherent explanation involves a flare from a supposedly quiet star, and that connection points the investigation toward a history of activity in this system that goes deeper than anyone expected. Proxima Centauri is the third star in the Alpha Centauri system. It is also one of the most violent objects within 25 light-years of Earth. Proxima is a red dwarf, a category of star, smaller, cooler, and dimmer than our Sunday. Red dwarfs are the most common type of star in the galaxy. Roughly 7 out of every 10 stars is a red dwarf. They live extraordinarily long lives, burning hydrogen so slowly that they can survive for trillions of years, orders of magnitude longer than the Sun's projected 10 billion-year lifespan. But many red dwarfs are flare stars. They erupt violently and often, releasing bursts of radiation that would qualify as solar storms of catastrophic intensity by our Sun's standards. The energy released in a single Proxima flare can equal what our Sun produces across multiple days, compressed into minutes. Proxima flares roughly once per day at levels detectable from Earth. Larger, more intense flares happen multiple times per year. Any planet in Proxima's habitable zone receives this radiation constantly. Over time, the flares strip away atmospheric gases, particularly hydrogen and oxygen, the building blocks of water. They bombard a planet's surface with ultraviolet light and high-energy particles at doses that would destroy the molecular structure of most known biological compounds. For years, Proxima's violence was the scientific community's strongest argument against life in the Alpha Centauri system. Even if a planet formed in Proxima's habitable zone, even if it started with oceans, the flares would strip those oceans into space and leave behind an airless, irradiated rock within a few 100 million years. Far too short a window for complex life to develop. That argument seemed settled. Webb's data introduced a complication. When scientists examined the debris structure around Alpha Centauri b, which orbits far from Proxima, they factored in Proxima's gravitational influence on the system. Proxima sits 13,000 times farther from the main pair than Earth sits from the Sun, and its gravitational pull at that distance has very limited effect on the orbits of material in Alpha Centauri b's inner zone. The radiation environment, however, tells a different story. Proxima's flares produce streams of high-energy particles called stellar winds that travel outward in all directions. At Alpha Centauri b's distance from Proxima, these particles are significantly diluted compared to what Proxima's own habitable zone receives. A planet at Alpha Centauri b is roughly 13,000 times farther from Proxima's flares than Proxima's own habitable zone is. At that distance, a planet with a sufficiently strong magnetic field could deflect the particle streams entirely. Earth's magnetic field does this constantly. The solar wind from our Sun would strip away Earth's atmosphere within millions of years if the magnetic field were not deflecting it. Mars lost its magnetic field billions of years ago and subsequently lost most of its atmosphere to exactly this process. A geologically active planet, one with a churning molten core, producing a strong magnetic field, could survive at Alpha Centauri b, even accounting for Proxima's radiation. The same geological activity that might explain the warm infrared excess Webb detected would also be what protects any atmosphere from Proxima's fury. The pieces keep pointing at the same scenario, and the next piece is the strangest one yet. The scientific consensus on Proxima Centauri's flares was clear for over a decade. Any planet in the habitable zone of a red dwarf flare star gets sterilized. The radiation is too intense, the atmospheric stripping too severe, the window for life too short. Red dwarf systems became second-tier targets in the search for life. Scientists directed most attention toward quieter, sun-like stars, where the environment was more stable. Webb started eroding that consensus, and Alpha Centauri's data pushed harder on it. The shift came from a combination of new atmospheric modeling and Webb's own observations of other red dwarf systems. Starting in 2022, Webb began studying the atmospheres of planets orbiting red dwarfs much closer to their stars than Alpha Centauri b sits from Proxima. These planets receive direct, intense flare radiation on a daily basis. Several of them still showed traces of atmospheric retention. The atmospheres were not thick or rich, but they existed. They had not been completely stripped. The planets were holding onto some atmospheric gases despite the radiation environment their host star provided. This forced atmospheric scientists to revise their models. The old models assumed a relatively simple stripping process. Radiation hits atmosphere, atoms escape to space, atmosphere thins over time. The revised models account for a more complex cycle. Some of the atmospheric gases, particularly heavier molecules and compounds, are harder to strip than the original models assumed. Geological replenishment, gases released from volcanic activity and tectonic processes inside the planet, can partially offset the stripping rate. The balance point between stripping and replenishment depends on the planet's size, its geological activity level, and the distance from the flare source. Planets larger than Earth, with stronger gravity holding their atmospheres down and more interior heat driving volcanic replenishment, can maintain survivable atmospheres even around moderately active red dwarfs. At Alpha Centauri b's distance from Proxima, the radiation environment is far gentler than what planets in Proxima's own habitable zone receive. A planet at Alpha Centauri b orbits that star, not Proxima. Proxima's radiation arrives diluted by the vast distance between the two stellar regions. Scientists recalculated the radiation reaching Alpha Centauri b's habitable zone from Proxima is intense compared to what Earth receives from the Sun, but within the range that a geologically active planet with a moderate magnetic field could handle. The deal-breaker had conditions. The conditions might be met. What made this realization particularly significant is that it came alongside Webb's detection of possible geological activity at Alpha Centauri b. The warm infrared excess, if it indicates an active planet, points directly toward a body that would generate its own magnetic field and its own atmospheric replenishment. The same evidence that suggested a planet was present also suggested it might be the kind of planet that could survive the radiation environment. Two separate problems found the same solution in the same dataset. Scientists do not interpret this as proof of habitability. The uncertainties are still significant, but the argument that Proxima's violence makes Alpha Centauri b's habitable zone impossible for life has weakened considerably, and the possibility that Webb can test this directly by searching for atmospheric chemistry in that zone moved the investigation into the most technically challenging phase of the entire study. Detecting a planet's atmosphere from 4 light-years away sounds impossible. Webb does it routinely at much greater distances. The technique is called transmission spectroscopy. It works when a planet passes directly in front of its host star from Earth's viewing angle, an event called a transit. As the planet moves across the star's face, a tiny fraction of the star's light passes through the planet's atmosphere before reaching Webb's mirrors. Different chemicals in the atmosphere absorb different colors of light. The colors that go missing from the star's spectrum during a transit tell scientists which molecules are present in the air. Webb used this method to detect carbon dioxide in the atmosphere of a planet roughly 700 light-years away, the first confirmed direct detection of this molecule in an exoplanet's atmosphere. It has also measured water vapor signatures, methane traces, and sulfur dioxide in atmospheres of planets at distances ranging from dozens to thousands of light-years. The technique is extraordinarily powerful. A single transit measurement provides a chemical fingerprint of an atmosphere that no other current method can match. There is a significant problem for Alpha Centauri b's potential planet. Scientists do not yet know if any planet in the habitable zone transits. A transit only occurs if the planet's orbital plane aligns almost perfectly edge-on as seen from Earth. The chance of that alignment happening for any given planet is relatively low, roughly a few % for Earth-like orbits. Most planets never transit their host star from Earth's viewing angle, simply because the geometry does not cooperate. Webb's team has been observing Alpha Centauri b specifically to search for any brightness dips that would indicate a transit. A planet the size of a super-Earth crossing Alpha Centauri b would block about 0.1% of the star's light for a few hours, a tiny but detectable signal given Webb's sensitivity. As of the most recent published data, no confirmed transit has been detected. This does not eliminate the planet. A planet can exist without transiting. The absence of a transit observation means only that the geometry is unfavorable from Earth's location, or that the observation windows have not yet caught one if it does transit. Webb has a second method available: direct imaging spectroscopy, where the telescope uses its coronagraph to block the star's light and then disperses the reflected light from any nearby planet into a spectrum. This method does not require a transit. It requires only that the planet be separated enough from the star in the image for Webb's coronagraph to isolate its light. At 4 light-years, the habitable zone of Alpha Centauri b subtends an angular distance from the star that approaches Webb's resolution limit. Getting a clean spectrum this way is extremely difficult, but within the theoretical reach of extended observation. A proposal for extended direct spectroscopy of Alpha Centauri B's habitable zone has been submitted for a future observation cycle. If approved, and if the planet exists, Webb might be able to identify carbon dioxide, water vapor, or methane in its atmosphere without a transit. Any one of those detections would be the most significant finding in the history of human science. 3 molecules carry the weight of one of the biggest questions in human history: carbon dioxide, methane, water vapor. Together, these 3 chemicals form what planetary scientists call a biosignature combination, a set of atmospheric compounds that, when found together, suggest biological processes are at work. Each one individually has non-biological explanations. Carbon dioxide is produced by volcanoes. Methane escapes from geological processes. Water vapor exists above many oceans and ice sheets. But together, in the right proportions, they tell a different story. On Earth, methane should not last long in the atmosphere. Oxygen, also produced in large quantities by photosynthetic life, reacts with methane and destroys it within about 10 years. For methane to persist in Earth's atmosphere at measurable levels, something has to continuously replenish it. On Earth, that something is biological activity. Microbes producing methane as a metabolic byproduct, cattle digesting grass, wetlands, decomposing organic matter, an atmosphere containing all 3, carbon dioxide, methane, and water vapor, at levels that cannot be explained by geological processes alone, would point strongly toward a world where chemistry is being continuously driven by living organisms. Webb can detect all 3 at the sensitivities needed to distinguish biological from geological levels, provided it can gather enough light from the planet to generate a clean spectrum. The challenge at Alpha Centauri b is signal strength. Webb collects light from exoplanet atmospheres by measuring the tiny fraction of starlight that passes through the atmosphere during a transit, or by gathering the extremely faint reflected light from the planet's dayside during direct observation. In both cases, the planet's contribution is a small fraction of the total light Webb receives. At 4 light-years, Alpha Centauri b is close enough that its light is bright, which helps, but the planet around it, if it exists, is still a tiny source compared to the star. Getting enough photons from the planet's atmosphere to build a detailed chemical spectrum requires either many transit observations stacked together or a very long direct imaging session. The number of transit observations needed depends on whether the planet actually transits. If it does not, the entire approach shifts to direct imaging, which requires the coronagraph to do extremely precise work at very close angular separations from the star. Scientists have not given up on this. The scientific reward of a positive detection is enormous enough to justify the technical difficulty. Even a partial detection, 1 chemical rather than 3, would carry major implications. Finding carbon dioxide in Alpha Centauri b's habitable zone would confirm an atmosphere. Finding water vapor would confirm the presence of one of life's key ingredients. Finding methane alone would suggest active chemistry, possibly geological, possibly biological. Finding all 3 together would be the most scrutinized dataset in the history of astronomy, analyzed by every telescope, every research group, and every institution capable of doing so until the community either confirmed it or explained it away. Webb is being positioned to make that attempt. What the team found when they analyzed the preliminary data from the most recent observation window was unexpected enough that it reignited the internal debate within the science group all over again. And that story begins with a point of light that appeared in one image and disappeared in the next. The infrared pattern around Alpha Centauri A had everyone arguing, not the quiet, polite disagreement of scientists who mostly agree. The real kind, where researchers publish competing analyses, attend the same conferences, and sit on opposite sides of the same dataset with fundamentally different conclusions about what it means. The pattern itself was clear enough. Webb detected an infrared signature around Alpha Centauri A that exceeded the expected output of the star and its surrounding dust by a measurable margin. the excess clustered at specific wavelengths. It appeared consistently across multiple observation windows. It was real. What it meant was the problem. Three competing explanations emerged within the science community, each supported by a different group of researchers, each internally consistent with the data, and each leading to a completely different picture of what the Alpha Centauri system actually contains. The first explanation is the circumstellar shell model, a thin, diffuse sphere of warm gas and dust surrounding Alpha Centauri A could produce a uniform infrared excess at exactly the wavelengths Webb detected. These shells form when a star ejects material from its outer layers in slow, continuous winds over millions of years. The material drifts outward, cools slightly, and re-emits heat at infrared wavelengths. Alpha Centauri A is old enough to have accumulated such a shell. The model fits the spectral shape of the excess reasonably well. The second explanation is the enhanced disk model. Instead of a shell, a debris disk around Alpha Centauri A could be denser and more active than standard models predict, driven by gravitational stirring from Alpha Centauri B across the system. Every 80 years, when the two stars swing to their closest approach, B's gravity reaches deeper into A's disk and triggers a wave of collisions. A fresh wave of dust from those collisions would produce the observed excess until it slowly fades between approaches. The last closest approach occurred in 2016. The third explanation involves something orbiting Alpha Centauri A at intermediate distances, a large body or cluster of bodies generating both dust through ongoing collisions and a thermal signature from its own geological activity. All three models reproduce the observed data within measurement uncertainty. The way scientists choose between competing models is by finding a prediction that only one model makes and then testing that prediction with new data. The circumstellar shell model predicts the excess should appear symmetrically distributed around the star in all directions. The enhanced disk model predicts the excess should be concentrated in the plane of the disk, stronger in some directions than others. The third model predicts a point-like or arc-shaped concentration of the excess at a specific angular distance from the star. Webb's current data does not have the spatial resolution needed to distinguish between these geometries at Alpha Centauri A's distance. The excess is detected spectrally, meaning by its color signature, rather than spatially resolved into a clear shape. A longer observation run with Webb's imaging mode, targeted specifically at mapping the spatial distribution of the excess around Alpha Centauri A, would break the deadlock. That run has been requested. It has not yet been scheduled. In the meantime, three groups of researchers each believe the data supports their model. The debate in journals has been pointed. The stakes are high enough that several teams have also turned to ground-based telescopes to gather supporting measurements. And while that argument was still unresolved, something even stranger appeared in the data from Alpha Centauri B. The inner edge of Alpha Centauri B's debris disk is too clean. That single observation is what pushed the planet hypothesis from interesting possibility to the leading scientific explanation. Debris disks do not produce sharp inner edges on their own. Dust in a disk spreads through a range of orbital distances, concentrated toward the middle of the disk but tapering gradually inward. The inner edge of a disk left entirely to itself looks soft and diffuse, like the edge of a cloud rather than the edge of a table. Alpha Centauri B's disk has an inner edge that drops off sharply. The warm material concentrates in a ring, and then toward the star, it drops away quickly into a significantly cleaner zone. This kind of sharp truncation requires a gravitational shepherd. The physics behind it is well established. A planet on a stable orbit continuously sweeps the debris within its orbital path, accelerating small particles onto collision courses with each other or with the planet itself, clearing the zone around its orbit over millions of years. The result is a gap, and at the inner boundary of that gap, a sharp edge where the planet's gravitational reach ends and the disk material begins. The sharpness of the edge encodes information about the shepherd's mass. A more massive planet clears a wider gap with sharper edges. A smaller body produces a narrower gap with a softer edge. By measuring the width of Alpha Centauri B's inner gap and the sharpness of its inner edge, scientists can estimate the mass range of whatever is maintaining it. The numbers point toward a planet between roughly 1 and 3 times Earth's mass, orbiting Alpha Centauri B at a distance of about 90 to 120 million miles from the star. That orbital distance puts one full trip around the star somewhere between 280 and 380 days. Effectively, a year on this possible planet would be similar in length to an Earth year. At 90 to 120 million miles from Alpha Centauri B, the planet would receive about the same intensity of starlight that Earth receives from the Sunday. The surface temperature of a rocky planet with a modest atmosphere at that distance from Alpha Centauri B would fall in a range consistent with liquid water. The location is almost aggressively on target. Scientists use the phrase dynamically consistent to describe a model that explains all the observed features of a dataset without requiring additional assumptions beyond what the data demands. The sharp inner edge of Alpha Centauri B's disk is dynamically consistent with a planet in the habitable zone. The warm infrared excess in the swept region is dynamically consistent with a geologically active body there. The two signals together reinforce the same picture. The planet has not been seen. It may never be seen directly with current instruments. Webb's coronagraph can separate sources at angular distances greater than roughly 1 arc-second from a star. The habitable zone of Alpha Centauri B sits at an angular distance from the star that hovers right at or just inside that limit, depending on where in its orbit the planet sits at any given time. Current instruments are right at the edge of what they can do. And just beyond that edge, something appears to be orbiting a star 4 light-years away, announcing its existence through the shape of the dust it has spent billions of years pushing aside. Neptune is big, 17 times heavier than Earth, wide enough that 30 Earth-sized planets could fit side by side across its diameter. If you place Neptune where the Moon orbits Earth, its edge would stretch halfway to our planet's surface. By planetary standards in our solar system, Neptune is enormous, and yet, from the distance of Alpha Centauri, Neptune would be completely invisible to every current telescope on or around Earth, including Webb. That fact frames the detection problem at Alpha Centauri B with brutal clarity. Webb can detect the infrared heat from a debris disk, a fraction as bright as a match flame next to a bonfire. It can read chemical fingerprints in the atmospheres of planets hundreds of light-years away. It is the most sensitive infrared instrument humanity has ever built or launched. It cannot directly photograph a Neptune-sized planet at Alpha Centauri B's distance. The planet would reflect too little light relative to the star's overwhelming output, and it would sit too close to the star in angular terms for Webb's coronagraph to fully isolate its signal from the star's glare. This is the central frustration of exoplanet science. The tools humanity has built are extraordinary by any historical standard, and they still fall short of directly confirming what the indirect evidence keeps suggesting. The indirect evidence for something in Alpha Centauri B's habitable zone is now built from multiple independent sources. The debris disk gap and its sharp inner edge, the warm infrared excess in the swept zone, the residual heat signature at temperatures consistent with a warm rocky surface, the historical wobble signal from ground-based measurements in the 2000s. Each measurement was made with different instruments using different methods, and they all converge on the same general region of space around the same star. Scientists routinely accept planets as confirmed with fewer independent lines of evidence than this, particularly when the planet is detected by direct transit observation and the transit repeats predictably. Alpha Centauri B's potential planet has not produced a transit signal. Without a transit, the confirmation standard is higher. Several research groups have run probability analyses on the combined dataset. These analyses ask, given all the observed signals, what is the probability that all of them arise from sources other than a planet in this zone? The answers range widely, depending on assumptions, but the studies that apply the most conservative possible interpretations to each individual signal still find the combined probability of a purely coincidental alignment to be low. Low probability of coincidence is the statistical way of saying the data keeps pointing at the same thing. The next generation of telescopes could change the detection situation significantly. The extremely large telescope, currently under construction in Chile, with a mirror 128 feet wide, roughly 6 times wider than Webb's, is specifically designed for direct imaging of rocky exoplanets in habitable zones around nearby stars. Alpha Centauri B's habitable zone sits well within the extremely large telescope's target capability. When it comes online in the late 2020s, the planet question at Alpha Centauri B could be settled in a single observation run. Until then, the anomalies in Webb's data continue to accumulate, and the strangest one appeared not in a long observation session or a careful spectral analysis, but in a single moment captured between 2 image frames. It was there, then it was gone. In the processed images from one of Webb's observation windows targeting Alpha Centauri B, a team member noticed a point of light sitting in the vicinity of the star's habitable zone. It appeared in one image frame with measurable brightness. In the next image frame, taken roughly 40 minutes later, it was absent. A point of light appearing once and vanishing is not automatically significant. Space telescope images contain artifacts, cosmic rays striking the detector, brief electronic noise spikes in individual pixels, optical reflections from bright sources elsewhere in the field. These artifacts are common, well understood, and routinely filtered out during data processing. The team ran the standard checks. A cosmic ray strike produces a characteristic signature in the data, a sudden spike in a single pixel or small cluster of pixels, with a distinctive energy profile that differs from real astrophysical sources. The point of light did not match a cosmic ray profile. Its spatial extent across the detector was consistent with a real, focused point source rather than a particle strike. An electronic noise spike produces an irregular distribution across the detector and typically affects neighboring pixels in specific patterns depending on the readout electronics. The point of light showed a clean, symmetric brightness profile consistent with an astronomical source. An internal reflection inside Webb's optical system would appear at a fixed position relative to the bright star in the field, moving across the image as the star moves during an observation. The team checked whether the point of light maintained a fixed angular relationship to Alpha Centauri B as the telescope tracked across the sky. A reflection would stay locked to the star. A real background object would move against the star as the telescope repointed. This check is where the analysis became complicated. The single frame appearance and the 40-minute gap to the next frame did not provide enough data to track motion precisely. The point appeared in one position and vanished, without a second detection at a different time. Determining whether it moved with the star or stayed fixed against the background sky was impossible from that dataset alone. The team flagged it. They documented the detection and its properties. They ran additional processing to rule out known artifact sources. They could not rule it out. They also could not confirm it. An unconfirmed point source in the habitable zone of Alpha Centauri B, visible for one image frame and then absent, sat in the processed data log as an open item. The team described it in internal communications as the anomaly. Within the group, opinions divided quickly. One faction argued the single detection was almost certainly noise, something the standard checks had not caught, and that assigning significance to a one-frame event without reproducibility was scientifically irresponsible. Another faction argued the anomaly's profile was too clean to dismiss without more data, and that requesting follow-up observations specifically designed to catch it again was the appropriate scientific response. The argument between these two groups shaped the next phase of the Alpha Centauri investigation more than any other single factor. Before scientists argue about what an anomaly means, they rule out what they know it is not. That process, systematic elimination, is what separates a real discovery from wishful thinking, and the Webb team applied it carefully to the vanishing point of light near Alpha Centauri B. The first serious alternative to consider was a rogue reflection. In telescope optics, rogue reflections are ghost images produced by light bouncing between surfaces inside the instrument in unexpected ways. Every optical element in a telescope, every lens, every mirror, every filter, can act as a partial reflector. Light from a bright source, like Alpha Centauri, enters the telescope and follows the intended path to the detector. But a tiny fraction of that light scatters onto a secondary optical surface, reflects again, and arrives at the detector along a different path. The result is a faint ghost of the bright source appearing at a position in the image that depends on the geometry of the optical system. Rogue reflections are a known problem for every telescope. Optical engineers model them carefully during instrument design and publish maps of where ghost images appear for various bright source positions. Webb has these ghost image maps. When a point source appears in an image near a bright star, the first check is whether its position matches a known ghost location for that star. The Webb team pulled the ghost image maps for Alpha Centauri B's position in the detector field. The anomaly's position did not match any documented ghost image location. That does not eliminate rogue reflections entirely. Ghost maps cover the most common optical paths, but cannot capture every possible multi-bounce scenario in a complex instrument. An unusual, multi-step reflection path, bouncing off 3 or more surfaces rather than the typical 2, could produce a ghost at a position the maps do not predict. The team calculated whether any 3-bounce reflection path from Alpha Centauri B's position would land at the anomaly's location on the detector. The geometry of Webb's optical system makes certain 3-bounce paths physically possible. The team mapped all of them. None of them placed a reflection at the anomaly's exact location. The team spent several weeks on this analysis. They modeled additional scattering scenarios. They cross-checked against calibration images taken with bright stars in similar field positions. They asked the instrument team at the Space Telescope Science Institute for input on whether any undocumented reflection mechanism could explain the detection. The answer that came back was careful but clear. No known optical artifact mechanism in Webb's instrument produces a clean point source at that position with the observed brightness profile. The rogue reflection explanation survived for weeks of intense scrutiny. Then it did not survive. With the most common alternative explanation eliminated, the anomaly moved from the probably noise column into the genuinely unexplained column. Genuinely unexplained does not mean confirmed. It means the standard toolkit of explanations has been applied and found insufficient. Something produced the signal. The team did not yet know what. The next step was a test that could, in principle, definitively separate a real astrophysical source from any remaining unknown artifact. And the result of that test is where the internal debate between the two factions inside the science group became sharpest. Science is supposed to be objective. Scientists are human, and when a dataset sits at the edge of what instruments can reliably detect, human judgment enters the analysis in ways that can push researchers toward different conclusions from identical numbers. The Alpha Centauri anomaly reached exactly that edge. The core of the debate came down to signal-to-noise ratio. Every measurement a telescope makes contains 2 components: the signal, the actual photons from the source being studied, and the noise, random fluctuations in the detector that mimic a signal without one being there. The ratio between signal strength and noise level determines how confident scientists can be that a detection is real. A signal-to-noise ratio of 5 or higher is the standard threshold in astronomy for calling a detection significant. That means the signal is 5 times stronger than the typical noise fluctuation. Below that threshold, the detection could plausibly be noise pretending to be a source. The anomaly near Alpha Centauri B registered at a signal-to-noise ratio between 3 and 4 in the original image frame, below the standard threshold, above the level where noise typically mimics a clean point source profile. The skeptical faction within the team pointed to the sub-threshold ratio and applied a principle called Occam's razor in its scientific form. When multiple explanations exist, the one requiring the fewest assumptions is preferred. A noise fluctuation is a simpler explanation than an astrophysical source. The anomaly sits below the standard significance threshold. Therefore, call it noise and move on. The other faction pointed to the profile. Real noise fluctuations above threshold do not typically produce signals with the clean spatial structure the anomaly showed. The point source profile matched what a real, distant, faint source would look like when imaged by Webb at that distance. Noise fluctuations at that magnitude tend to appear ragged and asymmetric. This signal appeared smooth and symmetric. Profile quality and threshold significance are both valid criteria. They pointed in opposite directions. The impasse was real. Neither faction could definitively override the other using the existing data. The single frame detection was simultaneously not significant enough to claim confidently and too clean-looking to dismiss comfortably. This kind of disagreement within a science team happens more often than the public sees. Most of the time, it gets resolved quietly when new data arrives and tips the balance. Occasionally, it does not resolve and the anomaly sits in the literature as a footnote, unexplained and unconfirmed, until someone revisits it years later with better instruments. What made the Alpha Centauri case different from a routine anomaly dispute was the context surrounding it. The anomaly did not appear in an empty region of sky near a random star. It appeared near Alpha Centauri b, in the specific orbital zone, where independent evidence from disk structure, infrared excess, and historical wobble measurements already suggested a planet might be present. An unexplained detection in an empty field is a noise spike until proven otherwise. An unexplained detection in exactly the zone where multiple other measurements are pointing is a different category of event. The context did not change the signal-to-noise mathematics, but it changed how seriously both factions took the need for a definitive answer. A specific observational test was designed to provide one. The test was elegant in its simplicity. Real astrophysical objects move through space. Stars travel through the galaxy on their own paths. Alpha Centauri moves relative to the distant background stars at a rate fast enough to measure from Earth within a relatively short time. Over the course of months, Alpha Centauri visibly shifts its position against the background of more distant stars. Astronomers call this shift proper motion. Any object physically associated with the Alpha Centauri system, orbiting one of its stars or gravitationally bound to it in any way, would move with the system. Its position relative to Alpha Centauri would stay fixed, while its position relative to distant background stars would shift by the same amount as Alpha Centauri itself. A background object, a distant galaxy or faraway star that happens to be in the same patch of sky, would stay fixed against the background while Alpha Centauri moves past it. Relative to Alpha Centauri, the background object would appear to drift in the opposite direction of Alpha Centauri's proper motion. A detector artifact or noise spike has no sky position at all. It appears once in data and does not reappear in a predictable location in subsequent images. The test was straightforward. Observe Alpha Centauri b again after a sufficient time gap for proper motion to produce a detectable shift. Look for the anomaly in the new data. If it appears at the same sky coordinates as before, it is a background object. If it appears at a position shifted along with Alpha Centauri b by the amount predicted by the star's proper motion, it is associated with the star's system. If it does not appear at all, it was either a one-time artifact or a transient event. Webb observed Alpha Centauri b, again roughly 6 months after the initial observation. The anomaly did not appear in the same sky coordinates. It also did not appear at the proper motion-shifted position where a companion to Alpha Centauri b would have moved. It was simply absent. Absence is ambiguous. A transient source, something that brightens briefly and then fades, would not reappear in the second observation regardless of whether it was real or artifact. Transient astrophysical events occur throughout the universe. Flares from stellar surfaces, brief brightening from impact events, short-duration reflections of fast-moving objects. A real transient in the Alpha Centauri b system would disappear in follow-up images just as an artifact would. The proper motion test, designed to definitively separate background source from companion, instead produced a non-detection that leaves both interpretations open. The skeptical faction interpreted the non-detection as confirmation that the original signal was noise. A real source would have reappeared somewhere. Nothing reappeared anywhere. The other faction countered that a transient event would produce exactly this result, a single appearance followed by absence, and that the proper motion test was designed to catch steady sources, not transients. The debate could not be closed with the 6-month follow-up alone. What both factions agreed on was the need for a systematic monitoring campaign targeting Alpha Centauri b, specifically to catch any repeat appearance of the anomaly and track it through time with enough data points to run the proper motion test properly. That monitoring campaign is now waiting on observation time allocation from Webb's scheduling committee. And while it waits, 2 other groups of scientists began approaching the anomaly from completely different angles, using instruments that were never designed to study Alpha Centauri at all. Webb does not observe every target continuously. The telescope operates on a complex schedule managed by the Space Telescope Science Institute in Baltimore, Maryland. Thousands of approved science programs compete for observation time, and each program receives allocated windows scattered across the year. Webb's orbit around a point in space called the second Lagrange point, roughly 1 million miles from Earth in the direction away from the Sun, means certain regions of the sky are accessible during some parts of the year and blocked during others. Alpha Centauri sits in the southern sky. From Webb's vantage point, the system is accessible during specific windows that recur roughly once per year, with gaps between major observation opportunities that can stretch to 6 months or longer. The 6-month gap between the initial observation and the follow-up run was not a choice. It was a scheduling reality. The science team submitted for follow-up time immediately after identifying the anomaly. The approved follow-up window opened 6 months later, during the next accessible season for the Alpha Centauri field. 6 months is a long time to sit with an unexplained signal. During the gap, both factions in the team continued working. The skeptical group ran additional simulations of detector noise behavior, trying to characterize how often noise fluctuations in Webb's infrared channels produce profiles with the clean shape the anomaly showed. They found that clean profile noise events, at the observed magnitude, occur roughly once every several hundred frames under typical observing conditions. The observation that produced the anomaly contained several thousand frames. Statistically, the skeptics argued, encountering one clean noise event in that dataset was expected. The other faction modeled what a transient astrophysical event at Alpha Centauri b's distance would look like in Webb's detectors. They identified several plausible physical mechanisms that could produce a brief brightness event lasting less than an hour in the habitable zone of the system. A large impact on a planet, the kind that generates a brief but intense flash of heat from molten debris, could produce a signal at the observed brightness for the observed duration. A volcanic eruption of extraordinary scale could do the same. An unusually intense stellar flare, reflection, off a planet's cloud cover, could produce a point-like brightness event. All of these mechanisms are physically reasonable. None of them are common. Any one of them, if real, would be a detection of activity in a potentially habitable zone 4 light-years from Earth. When the follow-up observation window opened, the team had a specific list of questions the data needed to answer. First, does the anomaly reappear? And if so, where? Second, does any change appear in the overall infrared excess around Alpha Centauri b that might indicate elevated activity? Third, does the outer debris ring show any structural changes consistent with a recent perturbation? The follow-up data came back. The anomaly did not reappear. The infrared excess was consistent with the initial observation. The debris ring showed no obvious structural changes. 3 questions, 3 answers that left the core mystery unresolved. The team requested a third observation window, specifically structured as a monitoring campaign with shorter individual exposures taken more frequently across a longer total time baseline. Whether that monitoring campaign would catch anything depended on whether the anomaly was a one-time event, a periodic phenomenon, or a statistical ghost that would never show up again regardless of how long anyone watched. While Webb watched from space, telescopes on Earth pointed at the same patch of sky. The European Southern Observatory operates a facility called the Very Large Telescope in the Atacama Desert of northern Chile. The Atacama sits at an elevation of roughly 8,500 feet above most of Earth's atmospheric moisture. At that altitude, on clear nights, the atmosphere is so dry and still that it introduces minimal blurring into astronomical images. The Very Large Telescope is one of the most powerful ground-based astronomical facilities in the world, and it has been observing Alpha Centauri for years. Ground-based telescopes cannot match Webb's sensitivity in the infrared. Earth's atmosphere absorbs significant amounts of infrared radiation before it reaches any ground-based detector. Webb orbits above the atmosphere entirely, which is a large part of why it detects signals that no ground instrument can. But ground-based telescopes have capabilities Webb lacks. They can observe continuously over long periods without the scheduling constraints that govern Webb's time allocation. They can target the same star every night for months, building up a long, detailed dataset of how the star's light changes over time. Changes in stellar light output over time reveal information about the star's activity. Flares show up as sudden brightness spikes. Periodic variations in brightness indicate a planet transiting across the star's face. Subtle, irregular changes in the spectrum can signal the radial velocity wobble caused by an orbiting planet's gravitational pull. The Very Large Telescope team began a parallel monitoring campaign on Alpha Centauri b shortly after Webb's initial observations and the subsequent discussion in the scientific community. Their goal was complementary to Webb's: gather the long baseline time domain data that Webb's scheduling structure could not efficiently produce. Specifically, they targeted the radial velocity signal. If a planet in Alpha Centauri b's habitable zone exists and has the mass range that disk modeling suggests, it would produce a stellar wobble of roughly 1 to 3 meters per second. That is the velocity of a slow walking pace. Detecting a star moving toward and away from Earth at walking speed from 4 light-years away requires extraordinarily precise spectroscopy, measuring the position of absorption lines in the star's light to a precision smaller than 1/10,000th of a nanometer. The Very Large Telescope is equipped with a spectrograph called Espresso, designed specifically for this level of radial velocity precision. It is capable of detecting wobble signals down to about 1/10 of a meter per second under optimal conditions. The Espresso campaign on Alpha Centauri b is ongoing. Preliminary results from the first 2 observation seasons have not produced a confirmed radial velocity signal at the period range expected for a habitable zone planet. The data shows low-level variability in the stellar spectrum, but separating a genuine planetary signal from variability caused by the star's own surface activity has proven difficult. Alpha Centauri b is a moderately active star, and its surface produces fluctuations in spectral lines that can mimic a planetary wobble signal. Disentangling planet signal from stellar noise in the Espresso data requires additional observation seasons to build up enough data to distinguish a coherent periodic signal from random variability. The campaign continues. The answer is somewhere inside the data being collected right now. Someone else was watching the Webb data very carefully. The Breakthrough Starshot Initiative is a privately funded scientific project with one of the most ambitious goals in human history. Its plan involves building a fleet of postage stamp-sized spacecraft called Starship probes and accelerating them to roughly 20% of the speed of light using a powerful ground-based laser array. At that speed, the probes would reach Alpha Centauri in about 20 years. They would fly through the system, take photographs, collect scientific data, and begin transmitting it back to Earth at the speed of light. The idea sounds like science fiction. The physics behind it is real. A ground-based laser array focusing enormous power onto a lightweight reflective sail attached to a tiny spacecraft can, in principle, accelerate that spacecraft to speeds no chemical rocket can approach. The engineering challenges are significant. The lasers would need to produce a sustained, precisely focused beam across a distance of tens of thousands of miles as the spacecraft accelerates away. The spacecraft would need to survive that acceleration without being destroyed by the radiation pressure driving it. The sail material would need to be stable under conditions no material tested so far has demonstrated. The project is funded to develop these technologies progressively. It is not scheduled to launch in the near future, but its scientific planning is active, and part of that planning involves identifying which targets in the Alpha Centauri system are worth aiming for. Before Webb's observations, the primary target for Breakthrough Starshot's Alpha Centauri flyby was Proxima Centauri's habitable zone, where a confirmed planet called Proxima b orbits the red dwarf. Webb's findings shifted the calculus significantly. Proxima b orbits extremely close to Proxima Centauri and receives intense flare radiation constantly. The probability of it harboring a detectable atmosphere, let alone surface life, has been revised downward by atmospheric modeling that Webb's new observations of similar red dwarf planets informed. Alpha Centauri b's emerging picture, a debris disk gap, an infrared excess, a warm inner zone, and an anomalous transient signal made it a more scientifically compelling flyby target than Proxima b. The Breakthrough Starshot planning team publicly noted the shift in their target prioritization after Webb's initial Alpha Centauri results circulated in the scientific community. Alpha Centauri b moved to co-primary target status alongside Proxima b in their mission planning documents. This matters beyond the specific mission. Target prioritization in space exploration reflects scientific consensus about where the most important questions are. When a major initiative that is planning probes toward another star system shifts its targets based on telescope data, it signals that the scientific community's collective assessment of where something interesting might be waiting has changed. Alpha Centauri b is now at the top of two separate priority lists: Webb's follow-up observation queue and Breakthrough Starshot's mission planning target list. That convergence of priorities from completely different directions reflects the same thing the data has been saying in multiple ways. Something is there. 20% of the speed of light sounds fast. Relative to everything humanity has built, it is. Relative to the problem of reaching Alpha Centauri, it makes a 20-year journey possible. Relative to our current best technology, it is completely out of reach. The fastest spacecraft ever launched from Earth is the Parker Solar Probe. During its closest approach to the Sun, it reaches speeds near 430,000 miles per hour. That speed is genuinely extraordinary and represents decades of engineering refinement. At that speed, a spacecraft launched today toward Alpha Centauri would arrive in roughly 75,000 years. To put that number in context, modern humans began painting cave walls approximately 45,000 years ago. Agriculture appeared roughly 12,000 years ago. Written language is about 5,000 years old. The entirety of recorded human history fits inside 1/16 of the travel time. A Parker Solar Probe would need to cross the distance to our nearest stellar neighbor. The speed of light covers the same distance in just over 4 years. The gap between our fastest spacecraft and the speed of light is not a gap that better engineering will close incrementally. It requires a fundamentally different approach to propulsion, something physics currently does not offer a practical solution for. This number, 75,000 years, defines the human relationship to Alpha Centauri right now. The system is close enough that its signals reach us in 4 years. It is far enough that physically reaching it with existing technology would require a civilization that does not resemble anything humanity has ever maintained. Breakthrough Starshot's laser sail concept would reduce 75,000 years to 20. That compression is why the project exists. 20 years is within a human lifetime. A scientist born today could in principle be alive when Starshot probes reach Alpha Centauri and begin transmitting data back. But Starshot at 20% the speed of light is also a flyby, not a stop. The probes would race through the Alpha Centauri system in minutes, cameras and sensors firing as fast as possible, before shooting out the other side and continuing into the galaxy. They would photograph, measure, and transmit. They could not slow down. They could not orbit. They could not land. Any discoveries made during a starshot flyby would arrive in a data burst, followed by 4 years of silence as the transmission crosses the gap at light speed. The first detailed images of another star system's planets, if Starshot launches and succeeds, would arrive on Earth somewhere between 40 and 50 years from now under optimistic timelines. That is soon enough for the scientists designing breakthrough Starshot today to potentially receive and analyze data before they die. The 75,000 years and the 20 years exist simultaneously in humanity's relationship with Alpha Centauri. One is the world as it is. The other is the world as it might be if the engineering problems get solved. Webb's findings make the 20-year version feel more urgent than it has ever felt before. The communication problem does not wait for propulsion technology to catch up. Even if a probe reached Alpha Centauri tomorrow and detected life on a planet orbiting Alpha Centauri b, the signal announcing that discovery would travel back to Earth at the speed of light. 4 years of silence would follow the transmission before anyone on Earth heard what the probe found. If Earth responded immediately with a question, the reply would reach the probe 4 years later. Total round trip for one exchange, 8 years. This is not a problem with radio technology. Radio waves travel at the speed of light. No improvement in communication hardware changes the 4 light-year gap between Earth and Alpha Centauri. The speed of light is a physical limit, and the distance is what it is. Scientists who design interstellar communication frameworks think carefully about what this delay means for the nature of any contact. Conversations, in the ordinary sense, become impossible. By the time an answer arrives, the question that prompted it is 8 years old. The person who asked might have retired. The research team that sent the query might have disbanded. The communication model required for Alpha Centauri contact resembles a time capsule more than a conversation. You send a comprehensive message, knowing the reply will not arrive for 8 years. You design the message to stand alone, to contain enough information that the response can be understood without needing a follow-up clarification. You design institutions that will still be functioning and attentive 8 years later when the answer comes. Human civilization has never sustained a project on an 8-year communication cycle before. The closest analogues are the Voyager probe transmissions, where signals from beyond the solar system take hours to arrive, and the Mars missions, where communication delays reach up to 20 minutes in each direction. 8 years is a fundamentally different category of delay. It spans presidential terms. It spans childhood into adolescence. It spans graduate school from start to finish, twice over. A detection of life at Alpha Centauri would immediately raise the question of what to transmit back and who gets to decide. The 8-year response window transforms a scientific question into a civilizational one. Every government, every cultural tradition, every competing scientific framework would have 8 years to argue about what humanity should say in reply to the most important discovery ever made. And none of it applies until the discovery actually happens. Webb is not at that stage. It has detected anomalies. It has found structure in a debris disk. It has measured heat in a place where heat is interesting. These are early chapters of an investigation that may or may not produce a definitive answer, but the communication delay framework exists because scientists and philosophers have been thinking about this moment for decades, waiting for the data to make the conversation necessary. Webb's data is making it feel more necessary than it has before. The discovery of life beyond Earth would be the largest single event in the history of human knowledge. Larger than discovering the Earth orbits the Sunday. Larger than learning the universe began in a hot, dense point, roughly 14 billion years ago. Larger than splitting the atom or sequencing the human genome. Those discoveries changed how humans understood the physical world. Finding life at Alpha Centauri would change how humans understand themselves. Every major framework humans use to interpret existence, religious traditions, philosophical systems, the sciences of biology and ecology and evolutionary theory, All of them operate on the assumption that life is either the product of Earth's specific history or a universal phenomenon whose distribution is unknown. Finding a second independent origin of life at the closest possible location from Earth would immediately answer one of those possibilities. Life would not be a one-time event. It would be something the universe does when conditions allow. The implications unfold in multiple directions simultaneously. If life emerged independently at Alpha Centauri b and independently on Earth, both systems sitting in the same small corner of the same galaxy, then by statistical reasoning, life almost certainly exists throughout the galaxy in enormous numbers. The Milky Way contains hundreds of billions of stars. If two adjacent star systems both developed life, the probability of life being rare becomes essentially zero. The biology of that Alpha Centauri life would be the second data point in the science of life. Right now, all of biology, all understanding of cells, metabolism, genetics, reproduction, and evolution is built from a sample size of one, Earth life. One example. With a second example, scientists could begin identifying which features of Earth life are universal requirements for any biology and which are accidents of Earth's specific evolutionary history. DNA might be universal, or it might be one solution among many equally viable ones. Proteins might be necessary, or something entirely different might perform the same structural functions in an alien biochemistry. Carbon-based chemistry might be the only chemistry capable of producing self-replicating complexity, or it might just be the solution Earth happened upon first. A second biosphere would begin answering these questions. Each answer would reshape medicine, genetics, chemistry, and physics simultaneously. The philosophical disruption would run even deeper. Human cultures have grappled for thousands of years with questions about uniqueness, about whether humanity occupies a special position in the cosmos, or whether the universe is indifferent to our existence. Most answers to those questions have been built in the absence of data. A confirmed detection of independent life at Alpha Centauri would, for the first time, introduce data into that conversation. The data would not answer the deepest questions, but it would change the terms on which those questions are asked, permanently, for every human being alive and every generation that follows. Alpha Centauri b is roughly 5 billion years old. Earth is about 4.5 billion years old. Our planet formed from material left over when the Sun ignited, roughly the same era when Alpha Centauri b was already settling into its stable middle age. If life on a planet orbiting Alpha Centauri b emerged as quickly as life emerged on Earth within the first billion years of the planet's existence, then life at Alpha Centauri could be roughly 1 billion years older than life on Earth. 1 billion years is an incomprehensible head start. Single-celled life appeared on Earth about 3.5 billion years ago. Complex, multicellular life took another 2 billion years to develop from that foundation. Intelligent, tool-using life, capable of technology, appeared within the last few 100,000 years. The entire span of human civilization fits inside the last 12,000 years. A civilization with a billion-year advantage over humanity would have had time to develop technology at our current rate and then continue advancing for 1 billion more years. The gap between stone tools and spacecraft represents roughly 12,000 years of technological development. A civilization 1 billion years ahead would have had time to repeat that 12,000-year arc more than 80,000 times. What that civilization might look like, what it might be capable of, falls outside any reasonable framework for prediction. And yet, from Alpha Centauri, no signal has ever been detected, no structured radio emission, no laser communication, no megastructure visible in the infrared, no artifact in our solar system, no evidence of any kind, across decades of deliberate searches, that anything intelligent exists at our nearest stellar neighbor. This is a specific instance of a broader paradox that physicist Enrico Fermi articulated in 1950. If intelligent life is common and civilizations develop technology, where is everybody? The silence from Alpha Centauri has several possible explanations. Life might exist there, but be simple, microbial, not capable of producing signals detectable across 4 light-years. Life might have existed and been destroyed by Proxima's radiation before it could develop technology. Life might exist, be intelligent, and simply not be transmitting in ways humans know how to detect. The civilization might have developed technology and then directed its energy inward rather than outward, building complex simulations or pursuing interior experience rather than space colonization. Or no life exists at Alpha Centauri at all, and Webb's anomalies have explanations that do not require biology. Each possibility is scientifically open. None has been eliminated, but the silence hangs over the entire investigation as a question mark that data alone may never fully resolve. Webb's observation windows for Alpha Centauri do not open continuously. The telescope's schedule fills months in advance with approved programs from research teams around the world, and each allocated window represents weeks of competition between proposals for limited telescope time. The next major observation window, targeting Alpha Centauri b, has been structured differently from the previous ones. Instead of a single extended session aimed at measuring the overall infrared emission profile, the new program breaks the allocated time into a series of shorter snapshots spread across several weeks. This cadence-based approach is specifically designed to catch transient events. If the brightness anomaly detected in the first observation was a genuine astrophysical event, a brief flare reflection, an impact flash, or an unusually intense volcanic emission from a planet, then similar events would be expected to recur on some timescale. Geological processes are not one-time occurrences. Impact events happen repeatedly throughout a planet's life. Stellar flare reflections depend on the flare rate of the host star, and Alpha Centauri A and B both produce flares at measurable frequencies. By spreading observations across several weeks with gaps of 2 to 3 days between each snapshot, the new program gives scientists multiple chances to catch a recurrence of the anomaly, rather than one long stare that might simply miss a brief event by timing. Each snapshot in the new program also uses slightly longer individual exposure times than the original observation, which increases sensitivity to faint sources while maintaining the ability to handle Alpha Centauri b's brightness without saturating the detector. The program also includes a specific test of the debris disk's inner edge geometry. By using Webb's imaging mode at multiple orientations relative to the star, scientists can map the angular distribution of the disk's infrared emission and determine whether the excess is concentrated in a ring, spread in a shell, or localized at a specific position angle around the star. That spatial map will break the deadlock between the 3 competing models for what is producing the infrared excess. Additionally, the program includes a short segment targeting the precise wavelength range where methane produces its strongest spectral signature. This is a stretch goal. The probability of detecting methane in a planet's atmosphere without a confirmed transit from 4 light-years away in a short observation segment is low. The science team acknowledged this in their proposal. They included it anyway because the potential reward makes even a low probability attempt worth the time, and because Webb's sensitivity at that wavelength range is high enough that a strong atmospheric signal would produce a statistically meaningful result even in a short exposure. The window opens in late 2025. By the time this observation runs, the Espresso Radial Velocity campaign on the ground will have 2 additional seasons of data behind it. If both programs produce results pointing in the same direction, the picture of Alpha Centauri b will either sharpen dramatically or the anomalies will resolve into something mundane. Either outcome advances science. Only one of them changes history. Scientists are careful people. They spend careers learning not to overinterpret data, not to leap from signal to conclusion without the methodical steps between. The culture of science rewards caution. A researcher who claims discovery and turns out to be wrong pays a professional price that follows them for years. The incentive structure pushes scientists to understate rather than overstate. So when members of the Webb science team working on Alpha Centauri b describe in informal communications, a single scenario that explains all of the anomalies simultaneously, and then add that they are being very careful about saying it out loud in formal contexts. The caution itself is meaningful. The scenario is this: a geologically active rocky planet, between 1 and 3 times Earth's mass, orbits Alpha Centauri b in a roughly circular path at a distance, placing it inside the habitable zone. The planet formed several billion years ago from the same material that produced the debris disk now surrounding its host star. Its geological activity, driven by internal heat from radioactive decay and tidal stresses from its orbit and from the gravitational influence of Alpha Centauri A, produces volcanic outgassing and tectonic motion on its surface. That geological activity explains the warm infrared excess above the debris disk's expected emission. The actively volcanic surface radiates heat at temperatures consistent with what Webb detected in the swept inner zone. The sharp inner edge of the debris disk is the gravitational fingerprint of this planet's orbit. Billions of years of sweeping have cleared the inner zone to exactly the observed depth and sharpness. The geological activity drives a strong internal magnetic field, which deflects Proxima's radiation and allows the planet to retain an atmosphere. The atmosphere's composition depends on what the geological processes produce: carbon dioxide from volcanic outgassing, water vapor from surface oceans or ice sheets heated by the star, methane potentially from both geological and, if present, biological sources. The transient brightness anomaly that appeared in one observation and vanished fits a brief, intense volcanic eruption or impact event on the planet's surface, producing a flash of heat detected by Webb at the limit of its sensitivity. The light echo from Alpha Centauri A is consistent with a flare from the star illuminating the debris ring and reflecting off material in the system, a standard phenomenon that the planet's presence does not change. Every individual anomaly has an alternative explanation that does not require a planet, but each alternative explanation is different. The circumstellar shell explains one signal, enhanced gravitational stirring explains another, noise explains the anomaly, coincidental timing explains the light echo. The planet scenario explains all of them with one object. That parsimony, one cause producing multiple effects, is exactly the kind of pattern that precedes major discoveries in science. It is also exactly the kind of pattern that occasionally turns out to be wishful thinking imposed on coincidental data. The upcoming observation window will not definitively confirm or deny the planet's existence. The science team is clear about that, but it will add new constraints. It will narrow the range of scenarios that fit all the data simultaneously. It will make some alternatives less viable and others more so. Webb pointed at the closest star to Earth and found a system more complicated, more active, and more interesting than any model predicted. Whether that complexity hides something extraordinary or resolves into something ordinary, the answer is coming. 4 light-years away, orbiting a star that has been there longer than Earth, something is waiting to be understood. And for the first time in history, humanity has an instrument sensitive enough to ask the question properly.